All right. So, this will be the tutorial for the lecture which covered the applications of. So, this is basically a tutorial where we are going to talk about some of the concepts. So, problems associated with some of the concepts that were discussed in the previous set of slides. So, in the previous set of slides we talked about the concept of creep and it is important in different industries, and we talked about the role of stress and temperature. We talked about characteristics of dislocations and how dislocations move when they face an obstacle and things like that. So, this tutorial is going to introduce you to some problems associated with the concepts discussed earlier. So, the first question is about nature of a barrier. So, let us go through this question. So, if the dislocation density rho is given by the following formula. So, rho is generally related to the inverse of the square of average spacing between dislocations. So, rho is equal to 1 over L square, where L is the average spacing between dislocations, and if the dislocation density is approximately 10 to the power 14 per meter square, what is the average spacing between the dislocations? So, that is the first part of the question. Now, if the atomic size is 0.5 nanometer. So, if the atom diameter is say 0.5 nanometer, how many atomic diameters does the spacing between the dislocations correspond to? And so, based on this, comment if the barriers to dislocation motion from dislocation stress field will be a long range barrier or a short range barrier. So, this question is about long range barrier or short range barrier. If you recall, long range barriers are those which cannot be overcome by thermal fluctuations, whereas short range barriers are those which can be overcome by thermal fluctuations. And we also talked about long range barriers being of the order of a hundreds of atomic diameters. So, because the distance over which the dislocation will have to overcome is a few hundred diameters, that is why it is long range, and short range is maybe a couple of a few atomic diameters, say ranging between a 1 to maybe 5 or so, and because they are so small in number, because the distance is so small in number, it can be easily overcome by temperature. Now, let us determine if this dislocation spacing will lead to a long range barrier or short range barrier. So, since rho is 1 over L square, this implies L square is equal to 1 over rho. So, that is 1 over 10 to the power 14 meter square. This implies L is 10 to the power 7 meter. Now, this is the average spacing between the dislocations corresponding to that atomic that dislocation density. Now, atomic size is 0.5 nanometer. So, how many atomic diameters does the spacing between dislocations correspond to? So, first let us convert this into nanometers. So, this is 10 to the power minus 7 into 10 to the power 9, that is equal to 10 to the power 2 nanometers. So, the average spacing between the dislocations is around 10 to the power 2 nanometer. So, 0.5 nanometer corresponds to 1 atomic diameter. So, 10 to the power 2 nanometers will correspond to 1 by 0.5 in 10 to the power 2, that is equal to 2 into 10 to the power 2 atomic diameters. So, the average spacing between the dislocations approximately corresponds to 2 to the power 2 into 10 to the power 2, which is 200 atomic diameters. So, so this is the effect. So, the long range stress field or the stress field because of the dislocation spacing is working over a distance of around 200 atomic diameters, which means for the dislocation to overcome it has to at least travel 200 atomic diameters. Since this is significantly larger than what we generally know for a short range barrier. So, this the internal stress field because of the dislocation is corresponds to a long range barrier. So, the answer to the question is that this is a long range barrier. So, that was the first question. Now, let us look at the second question. So, the second question is how do you choose a material for a particular high temperature application. So, if you know the service conditions, if you know the stress and the temperature at which the material is going to work, then you will be able to make a educated guess or choice for the material that you need to use for that particular application. So, this question is based on that. So, an industrial application requires the component to perform at a service temperature of 600 degree centigrade for with a service life of 10,000 hours. So, if you are given 4 different materials, so the 4 different materials are listed here: aluminum, zinc, magnesium and copper. Which of these materials do you think will be best suited for this application? So, the material has to survive a service temperature of 600 degree centigrade for at least 10,000 hours. So, which material of those listed below would you choose for this application and why? So, the answer is copper. So, the correct answer is copper, and now I will tell you the logic behind the answer. So, if you recall, the first thing that I said for creep is homologous, the concept of homologous temperature. I had introduced you to the concept of homologous temperature in the first few slides on creep. So, I was saying for a given temperature you have to determine the homologous temperature of the material, and if the homologous temperature is very high, then that material will not be suitable for the temperature at which your material is going to work. Now, let us compare the homologous temperature of these 4 materials. So, homologous temperature is given by T over Tm. T is the service temperature and Tm is the melting point of the material. So, now let us look at, we know the service temperature T is equal to 600 degree centigrade. So, we have to convert it into kelvins. So, this becomes 873 Kelvin. Now, the melting point of aluminum is Tm for aluminum is 660 degree centigrade, which means it is 933 Kelvin. Tm for zinc is 420 degree centigrade, which is 693 Kelvin. The melting point for magnesium is 650 degree centigrade, which is 923 Kelvin, and the melting point for copper is 1083 degree centigrade, which is 1356 Kelvin. So, if you now calculate for each of the metals the homologous temperature, you will find for aluminum the homologous temperature is 0.93, for zinc it is 1.25, for magnesium it is 0.94, and for copper it is 0.64. So, zinc, clearly the service temperature is higher than its melting point, which means zinc is going to melt at that service temperature and can automatically can be ruled out for that application. And for aluminum and magnesium also the T by Tm is very high. So, among all these materials, the material which has the lowest T by Tm or the lowest homologous temperature is copper, which means the material will have high creep resistance at that temperature, and within the listed metals copper could be chosen for this application. Of course, I am saying could be chosen, the reason is you will have one has to understand other aspects of the application including cost. So, industries are sensitive to cost. So, when you choose a material or propose a material for a particular application, you will also have to account for the cost of making a part with that material. But if we ignore those things including other environmental aspects such as perhaps the material needs to be also corrosion resistant or fatigue resistant, etc., etc. If we ignore all that and base our choice only on creep resistance, then for this particular problem copper is the answer, because it has the lowest homologous temperature among the lot. So, that is the logic behind the choice of copper. Now, let us look at the third problem. So, this problem relates to understanding vacancy concentration as a function of temperature. So, if the activation energy for formation of vacancy for a material is 200 kilojoule per mole, and if you want that the fraction of vacant lattice sites in the material be 10 to the power minus 6, then at what temperature should you equilibrate, at what temperature should you hold the material or equilibrate the material to achieve this fraction of vacancies. So, that is what the question is about, and to solve this question we are going to use this relation. So, n over n naught is approximately equal to e to the power minus q v over r t. So, q v is the activation energy for formation of vacancies. So, if you recall, this was something we talked about on the slide on point defects, especially with relation to understanding the interaction between dislocations and point defects. So, this relation is coming from there. So, Q V is the activation energy for formation of vacancies, and n over n naught is basically the fraction of vacant lattice sites. So, the problem then basically converts into following. So, you have to determine, take log on both sides. So, that becomes, so this implies ln of 10 to the power minus 6 is equal to 200 into 1000 divided by 8.314 into T. So, R is the gas constant which has a value of 8.314. So, if you use that, so minus 6 into so this implies temperature T will be 200 into 1000 divided by 6 into 2.303 into 8.314. So, that will turn out to be 1740 Kelvin, and so the temperature in degree centigrade will be 1467.9 degree centigrade. So, if you hold your material at that temperature for a significantly good period of time, then you will be able to achieve a vacancy concentration of 10 to the power minus 6 in your material. Now, let us look at a slightly different version of the same problem. So, in this problem we are talking about this problem is a slightly different, it is a variation of the earlier problem, in the sense that I am asking you to determine the activation energy for formation of vacancies, and what I have given you is different temperatures and the fraction of vacant lattice sites corresponding to these different temperatures. So, again we are going to use the same relation, n over n naught is e to the minus q v over r t, and what we are interested in knowing is q v. So, let us go to this Excel sheet. So, what you need to essentially do is take the temperature in Kelvin, take the inverse of it and plot the inverse of temperature against the fraction of vacant lattice sites. This is called an Arrhenius type of plot. So, when you do that, you will see that the data would more or less, when you plot the natural logarithm of the vacant vacancies concentration versus the inverse temperature, you will get a linear plot, and the fit for this data is given by the following equation here. So, you have the y axis as a function of x and with a constant involved. So, if you look at the exponential term, you have minus 20468 into x, and x we know is 1 over t, and so the other term is what is equal to q over r. So, 20468 is actually q over r. So, if you now go back, if we now come back to this slide. So, what we got from that fit is the value of q over r is equal to 20468. So, q over r is equal to 20468. So, q will be 20468 into 8.314. So, that turns out to be 170 kilojoule per mole. So, this is the activation energy for formation of vacancies in that material, and with this you can then determine the vacancy concentration at any other temperature of interest. So, that was the approach, that is this basically this problem tells you the approach to be used for determining the activation energy of vacancy formation in a material, and similar concepts will also be used in understanding creep and activation energy for creep. So, the next problem, since we were talking about dislocations, so the next problem is about understanding the nature of the dislocation. So, here a mixed dislocation is shown in the figure, and if the Burgers vector is represented by the arrow, what I want you to tell, so this is a dislocation loop, it has a mixed character, and so what I want you to tell me is identify at least a point on the loop which you think will have a screw character and a point on the loop which you think will have an edge character. So, that is what the problem is, and for this you need to go back to the portion where I introduced you to dislocations, and I was talking about screw dislocations and edge dislocations. And if you know the characteristic of an edge dislocation is a dislocation where the Burgers vector is perpendicular to the dislocation line, and a screw dislocation is one where the Burgers vector is parallel to the dislocation line. So, now let us look at this loop and find out which point, at least there are several points, but let us look at a couple of points. So, which point do you think will approximately correspond or which will be approximately parallel to the Burgers vector? So, this segment of this dislocation will be more or less parallel to the Burgers vector, which means any point on this segment can be called a screw dislocation. The segment on its whole can be called a dislocation, and any point on that segment can be will have a screw character. Now, let us look at a portion of the dislocation which is almost perpendicular to the Burgers vector. So, if you look at this segment of the dislocation loop, it is almost perpendicular to the Burgers vector. So, this means this portion of this dislocation, this segment would have an edge character, and so any point on this segment will also have an edge character. So, that is how you can determine the nature of a dislocation or the nature of a segment of a dislocation loop. So, now continuing in this with concepts on dislocation, let us look at let us visit the concept where we talked about the formation of breaks in dislocations. So, if you recall jogs and kinks, so we talked about the formation of jogs and kinks when dislocations intersect with each other. Of course, there are certain rules for the formation of a jog and for the formation of a break in a dislocation. So, we will discuss, we will get an understanding of that by solving this problem. So, here I am showing you two edge dislocations. These are edge dislocations because the Burgers vector is perpendicular to the dislocation line. So, you have dislocation line 1 and you have dislocation line 2, and they are going to intersect each other. So, the question is, what is the nature of the breaks that form in these dislocations. So, when these dislocations intersect with each other, so the arrow signifies the direction in which the dislocation 2 is moving towards dislocation 1. So, what is interesting is both dislocations will not develop breaks, only one dislocation will develop a break, and the dislocation that will develop a break is dislocation 1. That is because for a break to form, it is important that the Burgers vector B must be perpendicular to the dislocation. So, if you look at these two dislocations, the Burgers, so I am calling these 2. So, let me call this as dislocation 2 and this is dislocation 1. So, so we are looking at two dislocations, dislocation 1 and dislocation 2, and the question is about finding out which of these two dislocations, whether these dislocations will develop a break when they intersect with each other or interact with each other. So, for that the important point is that the Burgers vector of the intersecting dislocations must be perpendicular to each other, but if we look at the two dislocations here, what we see or what we note is the Burgers vector of dislocation 2, that is B2, is parallel to that of dislocation 1. So, the Burgers vector of dislocation 2 is actually parallel to dislocation line 1, which means 2 will not create any break in 1, whereas dislocation line 1, the Burgers vector B1 is perpendicular to dislocation line 2, which means dislocation line 2 will develop a break at the end of the intersection. So, this is what will happen after the intersection. So, this is how 2 will look like, whereas 1 will continue the way it was going. So, B2 and so this will be the break that will form in dislocation line 2. So, this problem was about formation of a break in a dislocation. So, the next question is about forces between dislocations. So, because of the stress field that is present around a dislocation, dislocations, those stress fields will ensure interaction between dislocations. So, this is one question about how the kind of forces that might exist between dislocations. So, you have two parallel and straight screw dislocations present inside a copper grain with a grain size of 0.04 millimeter, and now if the dislocations are separated by a distance of 120 nanometer, determine the total force on each dislocation if the dislocations are of opposite sign. So, the question is to determine the force acting between the dislocations. So, the force is given by G b square by 2 pi r. So, for copper we need to know G, we need to know the Burgers vector B. What is given is the distance between the dislocations, which is 120 nanometer. So, that is 120 into 10 to the power 9 minus 9 meter. So, for copper the shear modulus G is 40 gigapascal and the Burgers vector is 2.5 angstrom. So, the Burgers vector comes about from the crystal structure. Copper has an FCC crystal structure and you can find out the Burgers vector from the lattice parameter of copper, and so it is 2.5 angstrom, which is equivalent to 2.5 into 10 to the power minus 10 meter. So, with this information now we can determine the force. So, the force is force per unit length. So, this is equal to 40 into 10 to the power 9 into 2.5 into 10 to the power minus 10 square divided by 2 into 3.14 into the distance So, if you calculate this, you will see that the units, the force per unit length is 3.3 into 10 to the power minus 3 Newton per meter. So, once you do the calculation, that is the answer that you will get. Now, this is force per unit length. So, that is why you have the units as Newton per meter, but if you want to find the absolute force acting on the dislocation, then we will have to make a small assumption. So, we will have to assume the length of the dislocation. So, since the grain size of the material is around 0.04 millimeter. So, we can assume perhaps that the length of the dislocation can be approximately taken as 0.04 millimeter. So, that is 0.04 into 10 to the power minus 3 meter. So, therefore, the force, total force acting on the dislocation is 3.3 into 10 to the power minus 3 into 0.04 into 10 to the power minus 3. So, that will come out as 1.3 into 10 to the power minus 7 Newton. So, that is the total force acting on each dislocation because of the presence of a neighboring dislocation. So, this is how this problem involves you to use this relation G b square by 2 pi r to understand the force per unit length existing between two dislocations. So, with that I come to the end of the tutorial, and we will at a later stage we will do some assignments based on some of the concepts introduced in this first set of lectures. So, thank you.